OK, so hi, everybody. So after the first two talks, what I'm going to talk now is actually the time-space trade-offs, and specifically for inverting functions or inverting bijections, as Luca talked about, have connections that go beyond cryptography to other areas. And it turns out that these connections actually teach us something about lower bounds for function inversions, and also teach us something about those other problems in the other areas. So that's kind of the plan for today. And this is based on joint work with Henry, who is also here in the audience. So we've seen similar models in the past two talks, but let me just present the model as we will be treating in this talk. So what we want is we would like to construct algorithms that have black box oracle access to some function f. And throughout this talk, the function f will be from a set of 1 to n to itself. And for practical purposes, you could think of n as like 2 to the 128 if you want to think about some practical consequences. And such an algorithm gets as input a point in the image of the function. And the goal of the algorithm is to find any preimage of that point. And just to stress, the goal is to find one fixed algorithm that would work for all functions, or maybe on average for random functions. And this seemingly basic model actually captures few scenarios in cryptanalysis. So maybe the first example of just finding an image of a preimage of a hash function seems straightforward. But you can also cast other problems in cryptanalysis, such as known plaintext attacks on block ciphers, as well as applications to stream ciphers and password cracking. You can use these types of algorithms as a main building block for these types of attacks. And if this is the only thing you could do is kind of query the function, then it's not too difficult to show that the best thing you could do is the naive thing, which is just a brute force attack. So to invert a random function or a worst case function would take you time, which is roughly n. And as we've seen in the previous talk, starting with the work of Hellman, Hellman showed that you could do much more interesting thing if you consider a slightly more stronger model. And in this model, the inversion algorithm actually consists of two sub-algorithms. The first phase is a preprocessing algorithm. It can freely query this oracle at as many points as it wants. And at the end of the preprocessing phase, it outputs an advice string. And then in the online phase, the algorithm gets this one point in the image of the function. It gets access to the previously computed advice string. And it, as before, must output a preimage of that point using additional queries to the oracle. And this is useful for scenarios in which the function f is maybe some fixed function, or we would like to invert it on many points and amortize the cost across multiple inversions. And at least to a first approximation, the main two complexity parameters that we would like to optimize when considering these types of algorithm is the length of the advice string s and the running time of the online phase. And throughout this talk, when we will talk about the online running time, we will actually consider only the number of queries to the oracle, which serves as a lower bound to the actual running time. But in most actual algorithms of this form, the two are very closely related. So only some small factor distinguishes the two. So maybe by this point in this session, it shouldn't be too complicated. But let's just see a really simple example of such an algorithm, a particular setting of the parameters. So a preprocessing algorithm can simply query the function f at all points and store an explicit description of the entire function table in the advice string. So if the function is over a set of size n, such a description would take n log n bits. And then the online phase doesn't really need to query the oracle at all. It can just look up the point in the image in the table and output the preimage. And as Hellman showed, you can do much more clever stuff. So let's just look at the kind of the state of the art in terms of time-space trade-offs for this problem. And here we will have the space s on the horizontal axis and the time t on the vertical one. And we'll plot our trade-offs on a log-log scale. So it will be it will be simpler this way. So we have the two naive attacks. One is the online-only attack that you just query the function in online phase. You don't use any space. And the other one is just storing the entire description of the function in the advice. And what Hellman showed is that you can actually be sublinear in both space and time. So you can actually achieve all points on this curve s squared t equals n squared. So one particular point, if you set s equals to t, you get s equals t equals n to the 2/3. And other points on this line, you can achieve them as well. One caveat in Hellman's result is that, I guess two caveats in Hellman's result is the first one, that he gave more of a heuristic than a formal analysis of his algorithm. And second, that even this heuristic, he expected it to work only for the case of random functions. But then both these caveats have been closed in follow-up work by Fiat and Naor in '91, who first of all gave a rigorous analysis of this Hellman approach. And second, they also extended this algorithm to handle worst case algorithms and not only the average case with a slightly worse trade-off. So here, if you set s equals t, you would get n to the 3/4 instead of 2/3. OK, that's the upper bounds. What about lower bounds? And as Luca mentioned, the first lower bound that was given is by Yao in 1990, who showed that to invert. And here I won't go into much details in distinguishing random and worst case, but basically that the product of s and t needs to be greater than n. So this is this red line here. But maybe to see to clearly see the gap between the upper and lower bound, you can consider the case of the space being square root of n. So here, the lower bound only rules out algorithms that use less than square root n queries in their online time, whereas either Fiat Naor or Hellman's algorithm at this regime, square root n, which seems pretty reasonable, at least to me, they don't give any non-trivial running time. So this maybe just illustrates the gap. And so the main question that we were trying to study in our work is this question of optimality of Hellman's trade-off, or the upper versus lower bound question for this problem. And since these works that are here on the screen, there's actually been progress made on this problem and on similar problems. So I want to mention just a few of them. So in his work, Yao actually pointed out that Hellman's algorithm that was described in terms of function, when restricted to the case of random permutations or bijection, actually gives a better analysis that matches the lower bound. So when you want to invert permutations, we know the exact answer. St must be equal to roughly n. A set of practical improvements was given by Oshlin in 2003, and this is known in the practitioners community as rainbow tables. So this is these are various optimizations. In terms of lower bounds, in a work by Barkan, Biam, and Shamir, they showed that if we only consider a restricted class of algorithms that closely follow the approach of Hellman, then Hellman's algorithm is in fact optimal, and you can strengthen the lower bound. But this is only for restricted algorithms, and it tells us nothing about the existence of maybe a new class of algorithms that could potentially outperform Hellman's algorithm. Yes, I think this is for random functions.
So what kind of restriction is that?
So the way that the Hellman algorithm works is similar to what Luca presented, is basically iterating across the function. And so they have some model that captures algorithm that kind of sequentially iterate the function. And then there's been a long line of work, which we've heard about two of these works just now, that extend and study time-space trade-off for other cryptoanalytic problems to the random generators and so on, as well as introduce new powerful techniques that allow us to prove much more precise lower bounds for these and other problems. But even with this progress, the basic question still remains, and that is the question of the gap between the upper and lower bound for function inversion. And so what we do in this work, we actually study the function inversion problem through its connections to other areas in theoretical computer science, namely circuit complexity, communication complexity, and data structures. And each such connection teaches us something about either the function inversion problem or these other areas, or actually in both directions. So let me go over each of these connections separately, and then being in this workshop, we'll focus a little bit more on the circuit complexity connection. So the first result that we give in our work, we actually study a connection between the function inversion problem and various circuit lower bound questions. So in particular, what we show that to improve Yau's lower bound of ST greater than n would require us to prove new circuit lower bounds for a particular class of circuits called the Common-Bits circuits, which are I'll describe in a minute. And this is a class of circuit that was introduced by Valiant in the 70s. And actually, these types of depth, similar types of depth to circuits, have been instrumental to prove to point out connections and prove lower bounds in other areas as well. And one work that we actually build on in our work is the work on Brody and Larsen, who use connection to similar types of circuits to prove data structure lower bounds for certain dynamic data structure problems. And these circuits also, even kind of concurrently and after our work, they appear in connections to other lower bound problems. And the second part of this connection is that if we actually manage to prove a particularly strong form of lower bounds for the function inversion problem, not only this would result in lower bounds against this, some might say, a bit of a niche circuit model, a particularly strong lower bound would actually imply lower bounds against Boolean circuits, and specifically against linear size log depth circuit. And this is a major problem in circuit complexity that also dates back to Valiant in the 70s. And on these two connections, I will expand in this last part of the talk. And the bottom line maybe of these two connections is that to prove the optimality of Hellman's algorithm to improve the lower bound would require us to prove new circuit lower bounds. Yeah.
What about, so I don't know, I think maybe people would be happy also with the conditional proofs of these things, right? So if I believe that the circuit lower bounds exist, then do I get the Hellman optimality of the Hellman, or something that is I'm okay even with the singularity functions, it's
Right. So it turns out that here the connection is in one direction, which means that what we actually show is that if you could prove function inversion lower bound, you would get a circuit lower bound for a particular problem. So you would get a circuit lower bound for a particular problem, but maybe if you want to do the other way around, if you assume that certain lower bounds exist, the hard problems might not be the problems that we care about for function inversion.
I'm asking even more broadly, right? Was it even studied whether you can get this optimality in a conditional way?
So I think that we were.
It's hard, or it's like an approach that's in the literature?
So I can't recall now result of this form, but I agree this would be very, very interesting. So we tried to look at circuit complexity connections in the other direction, but we couldn't find any of the form you were saying. Yes.
So is there any reason to believe in the upper bound?
So let me talk about the other two connections. The short answer is there's not a good enough reason to believe that. So there might be better upper bounds. Yeah.
Basically, it might be hard to prove optimality of Hellman because it's not optimal.
Because it's not optimal. Yes, this is a possibility. Yes. But and in fact, I think that from the cryptanalytic problem, from the cryptanalytic perspective, improving the upper bounds would be super, super interesting. So yeah, I guess any progress would be great.
How strong the lower bound you need?
So I'll get to the quantitative result a bit later. Okay, the second set of results is that we actually show that even the existing inversion algorithms that we have, and particularly for permutations or bijections, actually result in new and better protocols for certain problems in communication complexity, in particular a certain variant of the pointer jumping problem. And the pointer jumping problem is a problem that has been studied for, I guess, more than 2 decades by now in communication complexity, with the original motivation being that showing communication complexity lower bounds would result also in circuit lower bounds that people have been interested in. But I guess that by now, these problems in communication complexity are kind of first-class problems on their own. And what we show here is that using these classic algorithms for permutation inversion together with this connection that we point out, we actually get the best known protocols for this variant of the pointer jumping problem. And specifically, whereas the previous bounds due to Pudlak, Rodel, and Sgal gives slightly below linear communication, using our approach, we can get something like n over k for k parties. So let's say when the numbers of parties square root of n, we get square root of n instead of linear. And a fair question to ask is this regime of square root of n, maybe it's kind of an artificial regime that's not even interesting for the problem, but actually this connection that implies circuit lower bounds is interesting exactly in the high number of players regime. So I guess this is, people are mostly interested in getting a lower bound in this regime, but we're kind of, the dual problem of understanding the best communication protocols is what we get. Yes? So if we can get better attacks, we will get better upper bounds for this problem. And actually, you can think about that if we make progress in the communication complexity front and improve lower bounds for pointer jumping, we would be able to improve lower bounds for function inversion. Yes?
So your first, just morally speaking, your first result is interesting if I think about it as the lower bound. And this result is interesting if I think about it as an upper bound. Is that right?
I think so. Yeah. I think so. Just because you get a better upper bound for some known problem, I guess this is the upper bound case.
Like improving the lower bound in the data structure, that seems hard because of what you said. Right?
Yeah. And then the last type of connection is a connection between also function inversion algorithm and certain problems in data structures. And in particular, the problem that we connect to is a simple text indexing problem called systematic substring search, which asks, this problem asks you to construct an index on a large string that then later allows you to efficiently search for short substrings within that large string. And what we actually show is that this problem has tight connection to function inversion, and again, doing the connection and then instantiating this connection with the best known algorithm, this time Fiat-Naor's algorithm for the worst case function inversion, allows us to get the best known data structure for this problem. And in particular, it's the first data structure that gets sublinear index size and sublinear query time. And some people who have been working on this problem, in particular Gall and Minterson, actually previously conjectured that maybe getting sublinear in both might be impossible. And using these cryptanalytic techniques, we show that you can get sublinear in both. Okay, so recapping the result, we've seen these three types of connection, and the main message being that if we can come up with better inversion algorithms, we will get consequences that go beyond crypto. So better communication protocols, better data structures. And on the other hand, if we manage to get an improved Yau's lower bound for function inversion, we will also get better lower bounds that in areas outside of crypto, in circuit lower bounds in particular. So in the remaining part of the talk, I will describe in more detail this connection to circuit complexity. Are there any questions about maybe the overview of the results? OK. So let's go back to this problem that was suggested by Valiant in the 70s. And this is a kind of a classic problem in circuit complexity that asks to find an explicit function from n bits to n bits that cannot be computed by Boolean circuits over the standard basis, let's say, of linear size and logarithmic depth. And maybe the slightly non-standard thing in this problem is that we are satisfied with finding a function that outputs n bit rather than a truly Boolean function that outputs only a single bit. And supposedly, I think that Valiant suggested that finding this more powerful, proving a lower bound for such a function would be an easier task than proving a lower bound for just a normal Boolean function. And in the same work that suggested this problem, Valiant actually suggested, the main technical part of that work was to suggest an approach towards hopefully resolving this problem. I know, he thought maybe in a few years this could be resolved, but this has been 40 years. And the approach was by introducing a kind of a different circuit model. And the hope was that in this different circuit model, proving lower bounds might be easier. And specifically, the connection that he showed that if all explicit functions have linear size, logarithmic depth Boolean circuits, then all such functions also have a certain notion of small circuits in the Commonbits model. And so the hope was, well, if we'll be able to rule out this, rule out small circuits in this seemingly simpler model, we will be able to get certain lower bounds for Boolean circuits. That was Valiant's approach. So let's see what is this circuit model that he introduced, often called Valiant's Commonbits model. So a Common-Bit circuit is a depth 2 circuit that consists of 3 layers of gates. And the interesting property of gates in this model that each gate can compute an arbitrary Boolean function of unbounded fan-in. So this seems very, very powerful. And in fact, if you place no restrictions on the wiring, then with such powerful gates, you can easily compute any function. But the restriction will enter through basically the limits that we will put on the wiring of the circuit. So let's now describe how such a circuit can be wired. So first of all, each of the gates in the middle layer, called common bits, and we count their number by W, so we have W common bits, can directly take as input all of the input gates, so no fan-in restrictions on the common bits. Similarly, each of the outputs can take all W common bits as direct input. So again, each gate can be connected to all of them. The main restriction comes from the fact that each output gate can be directly connected only to up to D input bits, and D is called the degree of the circuit. So the main 2 parameters that we have for such a circuit is the degree D, which is the number of inputs connected to each output, and the number W, the width W of common bits. And so this is the connection that Valiant showed that if all explicit functions have such circuits, then they have small circuits with a particular regime of D and W that I'm going to describe in a bit. And what we do in this work, we actually show that if all explicit functions have small common bit circuits, this means that there exists a function inversion algorithm that uses small space and small time. So essentially, if all functions have small circuits, there exists good time-space trade-off for function inversion. And the implication that we get in the counter-positive direction is that if we manage to improve Yau's lower bound, this would imply lower bounds for common bit circuits. And if we prove a particularly strong lower bound on function inversion, then the lower bound that we will get on common bit circuits will be actually sufficient to imply Boolean circuit lower bounds. And the reason that not every lower bound here gives some implication all the way up to Boolean circuit is because Valiant's connection only holds within some parameter regime and requires a relatively strong common bits lower bound.
The connection takes any circuit and transforms it into any small size, small depth circuit and transform it into
Common bits.
So it's 1 by 1. It doesn't use the fact that it's all.
Yes, that's true. Yeah. So let's see how does our reduction work. So what we do is essentially we define an operator that takes in n log n bits and outputs n log n bits, and we will call this the function inversion operator. And how does this operator act? The input to this operator of length n log n bits, we think of it as a function table of a function from n to n. And since it's a function from n to n, each entry in the function table takes log n bits to describe. So you can think of a log n log n bit string as a function table of such a function. And what the operator outputs is the function table of the inverse function. So in the first position, it would output the inverse of 1, and then the inverse of 2, and so on and so forth. And clearly, a function can have no inverses on some of the points, and there we artificially set it to 0 or some other constant.
When it's more than 1, then it's not an injection, it's not a permutation.
Right. You can pick any pre-image, and if you have no pre-image, you just choose 0 or whatever. This is how.
So if you pick a pre-image, then the function is supposed to compute that particular one. So the others are not acceptable.
Yes. I guess you can to make everything deterministic. You can say that this is the first lexicographically pre-image of that point. So what our theorem states is that essentially, if this one fixed operator, the function inversion operator, can be computed by a small common bit circuit, then there exists a non-adaptive, or let's say a function inversion algorithm that uses a number of bits of advice, which is the same as the width of the common bit circuit, and makes d log n queries where d is the degree of the common bit circuit. So the picture you should have in mind is that you start with a particular circuit for a particular operator, and you get from this circuit, you get this algorithm with preprocessing that inverts any function f. And actually, the reduction is not too difficult to describe. So we have this let's imagine we have this circuit, this common bit circle that computes the function inversion operator. Now I will show you how to build an algorithm with preprocessing. So we'll describe the preprocessing phase and then the online phase. So what the preprocessing phase does, so first of all, the preprocessing phase gets Oracle access to the function f. It evaluates the function f. It writes down explicitly the function table of the function f and plugs it in as the input to the circuit and evaluates the circuit. Then it takes this common bits layer of the circuit and just writes down the value of those gates, those W gates, as the advice. So the advice consists of these values. Then in the online phase, in order to compute the inverse of the function f on a particular point, what the algorithm does is evaluate the log n corresponding gates in the output layer. And to evaluate each such gate, you need the corresponding wire values, and then the wire values that go to the common bits, you know their values explicitly from the advice, and the remaining values that feed into the inputs, the online algorithm asks the little f function oracle for the corresponding values. And because in order to recover this value, you need to compute log n gates. This is where you get the log n blow up in the number of oracle queries with respect to the number of wires. And again, it's worth pointing out that kind of a similar approach to constructing data structures from depth to circuit also appears in this work by Brody and Larson. And so what we get now, we can state what we get now a bit more quantitatively is that if the function inversion operator has a common bit circuit with degree d and w, then we get an inversion algorithm that uses space w and number of queries d log n. And non-adaptive, yes, non-adaptive. And the corollary is that if we improve on this s times t greater than n up to polylog factors lower bound, we would get a similar lower bound for the function inversion operator in the common bits model. And
you can focus only on non-adaptive.
Right, you can focus only on non-adaptive algorithms. So presumably for non-adaptive algorithms, the job of proving lower bounds would be easier. And interestingly enough, the best lower bound that we have for a common bit circuit for any explicit operator in the common bits model actually matches, and up to maybe different logarithmic factors, matches the best known lower bound that we have for function inversion, which is d times w greater than omega n. And this is also from this work by Pudlak, Rodel, and Zgal in '97.
But you said this is not going to give you circuit lower bounds.
So in this regime, it doesn't give you Boolean circuit lower bounds. Only. So actually, the thing is that because we have better upper bounds, you cannot hope for a strong enough lower bound here that would be sufficient to prove circuit lower bounds for Boolean circuits. However,
what upper bounds do you have for non-adaptive?
Oh, that's a great question. So for non-adaptive algorithms, we actually don't know of any non-trivial upper bounds for function inversion. And as we've seen before, the Hellman-style algorithms are very sequential in nature. And so if you want to parallelize this algorithm, or taking it to the extreme, construct a completely non-adaptive algorithm, we don't know how to do anything non-trivial.
Can you even hope, like all these compression-style arguments use compression of random functions. Can you hope to get circuit lower bounds based on essentially the hardness of random functions? This is...
So those are random inputs for the circuit. Like the function is the input.
Yes, the random function is an input to the circuit. The operator itself is explicit. This is the function inversion operator. So it is not the operator for which you will get a circuit lower bound will be an explicit operator and not a random one.
So you said because it only needs lower bounds for non-adaptive, that's better. Also in your circuit, you said you can choose which pre-image you want. So that
Right.
also might make it harder to do and easier for proving lower bound. Yeah?
Yes, you have another degree of freedom, I guess, to play there. Okay, yeah. So just maybe to follow up on a non-adaptive question, because we don't have good non-adaptive upper bounds, we could hope for a much stronger non-adaptive lower bounds, and such lower bounds would be sufficient to prove circuit lower bounds for Boolean circuits. So if you want to focus on the
all the way through.
all the way through, exactly. So for
If you do some of the work, you give surprising lower bounds.
on Valiant model, exactly. Yeah. for circuit lower bounds. So there you need to prove a non-adaptive. You need a quite strong non-adaptive lower bound that uses space something like n log n over log n. So you need quite a strong lower bound, and t would be like n to the epsilon for any epsilon. Okay, so let me just conclude with some open problems on the upper bound front, if I may. One challenge might be to look at an intermediate case between arbitrary functions and bijections, and this and permutations, which would be one-to-one functions. So you can think about one-to-one functions from a set of size n to the set of size n squared. Which is not a permutation but a one-to-one function. And for many cryptographic applications, improving the upper bounds there would be sufficient. And again, we touched upon the question of parallelizable function inversion algorithm or non-adaptive function inversion algorithm. Both upper bounds and lower bounds, we don't have anything different from the general case. And that's it, and the paper is on ECCC.